we'll go through and then we will continue as we can, okay?
Okay, so good morning everyone. As you see, we'll continue now to talk about another type of neural networks. As you see here, we are talking about evolution. We started on the first day, on Monday, to explain a bit the foundations, starting from what a neuron means and also how a neuron works, how we can connect different neurons into layers and so on in order to build a neural network. And yesterday we have been focused on another type of neural networks, convolutional neural network, and we consider it as an evolution because of the nature of the data. What happens? The data are on different formats, and if I start to talk a bit about the different data formats that we have nowadays and so on, 80% of the data that it is produced nowadays is unstructured data. So we have structured data and unstructured data. What the unstructured means? The data are unstructured due to being into different formats, but also due to the data sources that they are produced. Unstructured data can be in textual format, it can be images, it can be video, it can be geolocation data, and so on. Most of the data produced from social media, they are unstructured data. And as I'm saying, 80% of the data being unstructured rather than structured data, like Excel files where the data might be considered as structured and so on, it means that we need to have in place some advanced techniques for storing this unstructured data, but also for processing this data and so on. And that is where the deep learning becomes powerful in handling this unstructured data. They are not usually, when we talk about unstructured, is the format itself that I'm saying, so it can be images, videos, geolocation data and so on, but it's also about that kind of nature of the data. This data, it depends on the data, but for example, the data coming from social media that we want to model, process, and so on, it can be that they are, we call it like connected data. What does that mean? The data that I'm going to process some data about Facebook, for example, the data connected data means that the data, rather than modeling this data in a relational database nowadays, we want to model it in another way in order to process in a better way. What does that mean? The data now, coming from social media, for example, we have data that belongs to actors. Every actor in social media or a Facebook account and so on can be a node. So rather than storing and processing all this data in a relational database, so what we have to do, we have to create some graphs. And these are connected data, and it makes sense that if now I store and model this data in a graph, so it will be nodes into the graphs, that these are the actors in the Facebook, so a person knows a person, and I'm going to have some relationship into it and so on. In this graph,
can we use the microphone because the back, people in the back cannot hear well? They say here it has a mic echo.
But I just need to
Yeah.
but I can also move.
Yeah. So if you can't hear, let us know, right? I understand that sometimes, people on the back cannot see, cannot hear, but feel free to interrupt.
And as I was saying, so we create this kind of graphs, and we have nodes that we are going to connect to the relationship and so on. So this is due to having these different data formats in region for and so on. It's not that now the problem, the challenge that comes with this data is not about how to model them in a proper way or in a better way, but it's also about how to identify patterns and so on. And yesterday we have been looking at one type of the data that are the image itself, okay? Because we cannot use neural networks that we can use it in order to do this kind of image processing and so on, but convolutional neural network, they comes with some advantages in terms of processing that image data that we have, and we're going to be looking at the example yesterday about the cats and dogs images and so on. Now, in today's session, we are going to focus on another type of data that are the sequential data now, and in order...
Luca? Ăla e figura. Nu știți?
Ou não precisa ficar em problema, porque por todo jogo assim não faz problema.
Am despat nu să cum
É ok. Okay. I don't think we had any issue yesterday,
Yeah, I know.
They had the issue actually
We
hearing.
had,
Not us.
okay. But,
Maybe you know we get tired the third day.
Okay.
We don't want to hear anymore.
Depressive. Should we wait or
Huh?
should we wait or?
Hold on. Can we make the microphone work?
But I have the slides here. I'll try to be loud. I can.
I mean, this is any microphone that you on. We want to use them.
Yeah. Okay, so I'll continue and I'll try to speak loudly. So today we focus in another type of data. We have sequential data now that we cannot handle and process in a proper way using these different types of neural networks that we have been looking at in the first and second day. And we are talking about another type of neural networks, which are recurrent neural networks, and we use that for sequential intelligence. But let's have a look now. So you see in here that I have a sentence. The sentence itself is the movie was not good. And if we want to do some sentiment analysis, what is a sentiment analysis in NLP? So let's suppose that you own a hotel or a business and so on, and you are getting some reviews. You want to process these reviews. If there are thousands of reviews, you are not going to read each of these reviews in order to understand what the clients are talking about, if they are positive or negative and so on. So you need to have to process them in a way in order to understand about the sentiments. And what you have, you need to now process this textual data, let's say, that every customer provides to you, and you want to classify the classification process itself into sentiments. What kind of sentiments? Is a positive sentiment? Is a negative sentiment? Or is it is a neutral sentiment? So, three classes. This is a classification problem of three classes. But now you have textual data that you have. It can be a single sentence, one line. It can be thousands of sentences that you have to process and so on in order to classify to positive, negative, or neutral sentiment. There are different ways of doing it in NLP. Myself, I introduced to students some ways about calculating the polarity. So we use some models that they calculate the score, let's say, for each of the sentence. If the score is that polarity is greater than 0, it will be classified as a positive sentiment. If the score is less than 0, it will be classified as a negative one, and if the score is equal to 0 or almost 0, so we say this is a neutral sentiment and so on. Looking at this sentence, the movie was not good. If I'm going to process that one with the approach that we did the first week, having that neural networks and so on, we are not keeping any memory there at all, so we have not talked about memory at all. And if we are going to process it, so what it will be the sentiment that we'll get? Negative. It will be a positive, a negative, or a neutral? It has to be a negative. It has to be a negative because you are, why? Why you don't think that it will be?
Negative sentiment.
Yes, but if I'm going to the pipeline where I don't have no memory at all, so I'm processing all the words, I don't keep, so I process the first one, it's going to be, for example, a neutral one. The movie, neutral, was neutral, not, it will be a negative one, but after that, when I move to the next one, to the next word, that it will be good. Good is a positive sentiment. So the output that I'm going to get, with all the methods that I've been looking right now, you see now the previous pipeline, so it will be what? It will be a positive one that I get, because I'm not keeping any memory. Yourself, you are saying to me that this is a negative one, because now what? You go back and you see that, oh, before the word good, there is that not. So this is the concept of memory now. You are doing yourself now. But if you go back to the neural architecture that we are talking right now, we have not introduced any memory at all. So no memory. So the output that I'm getting, if I analyze this sentence and I want to do this sentiment analysis, it will be good. Not, it will be a positive sentiment rather than a negative one. Why? Because we are lacking now, we don't have any memory mechanism in place. in order when I arrive or achieve at the word good to process, I need to know the previous words that has been in the sentence in order to get a context of that one and to end up with a correct sentiment class. And in this case, it will be a negative one that we are doing. So this is the main idea behind what the recurrent neural network do. So now we want to have in place, or we want to modify a bit that unit of the neural network now, in order to make it possible to have memory. So this is behind the recurrent neural network. How we can modify the architecture that we have been looking at in order to include memory. And what happens? In terms of the sequential data that we talked, here you have different types of sequential data. And the first one is elements appear in order. Okay? Can you give me an example when the order of words matter in a sentence? I want an example. Yeah. So, for example, if I say, a man beat a dog beat a man, does the order
Matters. Yes.
matters?
Yes.
Okay. So that is important. So now, the meaning changed totally. A man beat a dog beat a man. The order matters in this. It's a very simple example. And that is why we say that the first rule in order to have sequential data is the elements appear in an order that makes sense and matters. Okay? The second one is about earlier information influence later information. Yeah. And this is the example of the review. So now good, but this is not a positive sentiment. It's a negative. Because what? The previous elements now in the series of data that we have, and I'm saying series because you see there time series as well. So it matters. So not now matters to the good one, and we need to end up with a negative sentiment rather than a positive one. In here you see that language and text and all the examples that we are bringing, so we need to use that one, this type of data for translation, for sentiment analysis, for chatbot and so on. And tomorrow we are going to focus a bit on introducing the main concept behind generative AI and chatbots and how they work and so on. We have audio, another data type that we want to process. In this audio we do speech recognition, voice assistance and so on. Time series data, most of you comes with your background in statistics and you know about working with time series data for forecasting, for RNN detection, and also we use it for stock prices and so on, but also in biology it matters. Can any of you tell me why in biology we have sequential data? What are the sequential aspects in biology? From the data set that we have.
Or DNA.
The DNA, right? Letters in the DNA matters. The sequence of letters matters in the DNA. So these are the different types of data that we have, where we have where the elements appear in the order that matters, but also it's important to understand that earlier information influenced the current state. Okay? So, but let's have a look now to understand the unit. Okay, how is the introduction of memory? I grew up in Greece. No, I grew up in Albania. So I grew up in Greece and I speak fluent. I need to predict the next word. What it will be the next word? I grew up in Greece and I speak fluent Albanian.
No, Greek.
Why?
Because of the context.
So you are reading it and you are memorizing. This is. So now we want to imitate what humans are doing, like our memory, but now we want to enhance the network in order to provide the memory aspects to it. The same as we do. So you read the sentence, I grew up in Greece and I speak fluent Greek. Okay? So what happens in here? So once we achieve the Greek word, there is a language context in here that it is extracted in here, and we call it context thread. And now the hidden state in here, and I'm talking about later about the neuron, is the mechanism that carries that context of Greece and is now predicting and just figuring out that the missing word at the end of the sentence it will be Greek, due to that hidden state Greece here. So this is the concept behind the recurrent neural network that we want to implement. How to do it, let's say, and how we change this unit. Let's go back now to the cell. So this is the recurrent neural network cell. Now I want you to answer me about how many how many lines do I have, or how many cross connections? Yeah, how many connections do I have over time?
4, right?
No, wait for.
Because you are within, I mean, from
It
the
appears
cell
to in the
to
picture,
cell.
but this is one as a concept, let's say. How many connections do I have in this one? In the previous neural network, we have been looking at two connections. There will be an input going into the network, something happens there, you know, the net sound activation function, and there was an output. This was the simple unit that we explained on the day one. Okay? So now you see here that we have 3. Don't get confused about having 2, let's say, but in terms of connections, 3. So,
In terms of
yeah, it's okay, yeah, I got it. So now what happens? There is a current input. In this example, it will be a word, let's say good, for example, the last word that we had in the sentence about the movie and so on. And now, in the cell, what happens? There will be an output, and the output itself is going to be a hidden state that is going to be feeding in the next neuron, because now these are neurons, but they are still connected, okay? But what happened? We see that we have a new connection now, which is the hidden state. What is the hidden state? The memory itself. We are talking about memory now. You memorize when you read the sentence, the GRUs, and after that, using that word that you memorize of GRUs, you fill in the missing part that it was Greek. So, okay, that I speak Greek. So the same happened here. The previous now memory, or let's look at it mathematically. There is a simple formula in here that everyone can easily understand. So the current input that we get the word is going to be blended now, okay, with the current word that we get, the input, is going to be blended with the hidden now state, and is going to produce the output that it will be a hidden state that is going to be feeding in the next neuron. Did you get it? Okay. So let's look at the whole picture, how it looks in a sequence. Here, unrolling, time step by step. So, do you want me to explain, or any of you can explain how it looks like? The first one, neuron 1, we are going to get now, instead of processing input independently now, we are looking at the network, how it carries through time. You see, we have the T1, T2, T3, and so on. So, in the first one, what we do? We are getting the first word in here, or the input. Okay, so this is the first input. Okay, it goes in the cell. Do you have any previous? Do you have memory that was?
H0 hidden.
No, it doesn't have. It's the first word. So you start the sentence. I was born. So I was here. Okay, so it doesn't have. Let's say so. Nothing to blend with the previous one. Okay, it's going to produce now that hidden. The output here, it will be a hidden one that is going to the next layer, next unit, okay? And now, the new word is coming in the sentence, I was, it will be was here. It's going to be blended in again in here, and it's going to output something to the next one and so on, okay? So, this is the concept behind the recurrent neural networks. But this is a very interesting picture to look at, and I want you not only to think about many to one, one to many, and many to many, but also to think about these different types of mapping sequence architectures where they are relevant to be used with different applications and so on. In the first one, what we have, we are going to read a review, like the movie was good, the movie was not good, and so on. So now what we do? We are going to read the sequence. The input, it will be a sequence of words, okay? X1, X2, X3, and so on, all of them. But what is the purpose? What I want to do? I want to do sentiment analysis. So the output that I want to get now, it will be classification, 0, 1, or 2, belonging to 3 different classes of the sentiments, positive, negative, or neutral sentiment. So that's why I say many to 1. So read. So there will be a sequence of words to read. But what? I'm going to process them, and the Y out, it will be just one, You see there is a note, only one note there, because what I'm doing now in the sentiments. So I'm going to output, in this example, it's a binary classification, positive and negative. I'm excluding, I'm not interested in getting them to process, to figure out the neutral ones and so on. So I want to do a binary classification of sentiments and sounds. So this is in here that we have sentiment analysis, okay? So you have text, a list of a string of words, or bytes, and now you are going to process it, and the output that you will get after that, it will be just the positive or negative sentiment per that specific text or sentence. I'm talking sentence as a simple unit in order to process it. Is that the first architecture clear? So that is many to one. Now if we go to the second one, in the second one we have one to many now. Okay, so what does that mean, one to many? You see there are some hints there that you can also bring some examples in terms of this type of architectures. Where do you apply it? You have an idea? Can you give me an example? Yes, please. It says about
It was a prompt, and then the output can be one sequence or many sequences, so many.
So, everyone is using now ChatGPT and so on. You talked about prompts, so what you do now? You are going to input a prompt, so generate something. You say generate an image or a text and so on. So this is one, we say it as an input, it will be the prompt itself, what you are asking the chatbot to do. And after that, the output that I'm going to get, it will be a sequence. So it's going to generate a large text depending on my prompt. Yeah? And this is the architecture of one to many. It will be one prompt, and I'm going to get a text depending on what I'm asking and so on. Okay? Yeah? Any questions?
Yes, a small question about mathematical with y1, y2. How are they computed? I mean, I know the formula for the HTs.
No, this is just what happens in one unit in here.
Okay, and what about the y, the final, the outputs?
The final output in this one, it will be a classification problem. So it's just going to classify if it's a positive or not. So what we get. Okay? So it's about the architecture itself. So what we are talking about how the architecture works. What it will be the input, and the input in the first one it will be a sentence, for example, which is a sequence, let's say. And after that the output is going to, it's a classification problem, but a binary one, where we are going to classify the records or the sentences that we have, if they belong to a positive sentiment or if they belong to a negative one. So this is the architecture here. Okay? But in terms of how these recurrent neural networks and so on, so how the LSTM works, we are going to open the black box in the next slide. So I continue to keep it as a black box for the moment, and later on I'm going to open it a bit more mathematically. So let's have a look to the other one, which is many to many now. Okay? So I want you to think about that one and bring an example. You see that there is a machine translation in there, so we are going to have an input sequence, and there will be again an output sequence. So a sequence to input, but you see that also, so the sequence, what it will be the sequence? X1, X2, X3 and so on. And after that, as output, I'm going to have again a sequence. Y1, Y2, Y3. So think about the example that you have to, I don't know if you have started to work on the project, let's say, but in the project that Zois has drafted, we want you to work on with translation from English to Albanian and so on. So can you think about why we are having a sequence as an input and what it will be the output as a sequence in terms of the articles that you have? So can you elaborate a bit more that with the example of the project? So this is what I want to hear from you.
The input is sequence of sentences.
So what it will be?
Sentences the articles in English.
It will be a sentence in Albanian.
Yes, sentences in Albanian.
So now you want an architecture in place that is going to process this sequence, but the output that I'll get at the end, and I'm getting what it will be. It will be still a sentence, but it will be in English, because I'm doing translation. Yeah, it will be different. Yeah, it will change place. It doesn't mean that, okay, in terms of visualization, in here, it's just to visualize. I'm going in the sequence, I'm having 3 words, let's say, X1, X2. I speak Albanian. Okay, so this is a sentence. Now, when it comes to the output in here, that I'm going to do the translation, maybe I'm not ending up with having exactly 3 words again, okay? Even here, we represent it like having only 3 nodes and 3 nodes, but it doesn't mean that it will be like that. It depends on, yeah, okay? Yeah, it depends on the input and it depends on your output, but here we are visualizing this way just to provide you the idea that this is a many-to-many architecture. Okay? So, and this is in translation. So, what you have to keep in mind for the moment, because as I explained, there will be some other slides that we explain in details and mathematically, and the next one is about, we are having an input sequence, and we are having an output sequence. Okay, but don't think that the input sequence and the output sequence, they are identically, even in the terms of the number of words that we are having and so on. It will be different, because if I'm going to translate, so there will be differences in the sentences that I'm getting from one language to another and so on, okay? Yeah? Any questions?
There is one.
Yeah. But here we have also this, we call it encoder, and we call this decoder and so on, but I'm not talking right now for the moment, okay? How this happens, the process in itself. It's just to give an idea about the mapping sequence architecture that we have. So, this is an important slide that you have to understand. And this is also behind the idea how we can, what happens with when we include this memory, and how we have a big challenge in here, and how can we handle this challenge? We're using the LSTM, one type of recurrent neural network. They are widely used, they are powerful. We use a lot in terms of doing text processing and so on. When I talk about sentiment analysis myself, as I mentioned, there are some techniques that we can use in order to do sentiment analysis, like polarity. We calculate some numerical values, and they are positive polarity, they are negative polarity, and so on. But there are other neural networks. This is not based on the neural network at all, as an approach. But in order to do that sentiment analysis, you have a text, you have to clean that text, and cleaning the text means remove stop words, remove punctuations, you have to do the lemmatization, so each of the words has to be converted to a dictionary word. For example, study, all should be transformed to stud and things like that. And after that, we can calculate the polarity and we do all this sentiment analysis. There is another approach that rather than using that polarity calculations, we need to create an LSTM that I introduced now, which is a type of recurrent neural network that is doing and taking care about understanding the context of my data that I have, but also is ending up with classifying the data into different sentiments, positive, negative, and so on. So now in here, the gradient crisis, this is something important to understand. When we have that memory now, okay, because we are introducing the memory concept, the state now, in our nodes, and when we do the back propagation process, we need now to multiply different numbers, because we are going back now. So if I want to go back, the memory from 50 plus words earlier in my sentence, I'm moving back now in order to keep the memory. So what you did when you read the sentence about Greece, so you went back, okay, and you, because you memorized Greece, and you predicted Greek, okay, so you went back. The process of when going back is the process that now we need to multiply some numeric values. Let's suppose that these values are very small, 0.2. So now if I go back and the memory from 50 plus words earlier now, 0.2 multiplied by 0.2 by 0.2 by 0.2 is 0.2. So what I will end up, what kind of value I'm getting?
Very, very small.
Very, very small, close to 0, almost 0. So what does that mean in this case? So Hamming gradient, you see, it fades. Now, there is also the opposite problem on the other side. So I'm now bringing the challenge that exists with recurrent neural networks. So you remember now the unit? And in that unit, I told you that we want to bring the memory, the hidden state. But bringing the hidden state we end in this situation. So when the numeric values now that we want to go back to 50 plus words, for example, are very small, I can have a problem of vanishing gradients, okay, due to this small values that when we multiply them during the propagation, so the gradients vanish if we end up to really close to zero. This is a problem. But there is also another problem on the other side. What does that mean? You see, there is an exploding gradients, which is the opposite case. So when these values are bigger, 1.5, and you still move again 50 plus words earlier now in the sequence, so you are going to multiply this 1.5 by multiply by 1.5 and so on. So what happens now? There will be an exploding gradients on the other side. So now we want to be in something in that, in order to get the thread of context, we want to be in the middle and to avoid these two situations when we can end up with having a vanished gradients or we can end up with having an exploding gradients.
These values decrease according to how much back we go?
Yes. So because if we want to go back memory from 50 plus words, because we are talking about cases that we process large amount of data, okay? It's not about a simple sentence, the movie was not good, okay? When we say 50 plus, so it means that we have a big corpus of data that we want to keep memory now. But we can't memorize everything, so this is the idea here. So we can't memorize everything. Because if we memorize everything, so we can end up with these situations, which can be a vanished gradients or it can be also an exploding gradients. Okay? So now in this situation, so what we are doing, why we bring it here? We want to keep memory, we need memory in order to understand the sentence, we want to go back and keep memory, but there are also some issues. Okay? So if we keep the whole memory, so we don't delete anything, let's say, or we don't forget anything, so we can be in situations that if we keep the whole, so we can or have vanished gradients, or sometimes we can have exploding gradients and so on. So now, okay, so maybe we have not to memorize everything. Okay? So let's see how now we can have another mechanism in place in order not to memorize everything. And this is where the solution comes. There is a type of recurrent neural network that deals with this problem of the gradient that I was explaining. And this is the LSTM, long short-term memory. Okay? So the LSTM in here, in the next presentation I focus on explaining in more detail the LSTM, not like a black box. But now what it does, it controls the memory updates of the network in order to remember longer context, but improving. Now what happened? You see that the LSTM is going to have 3 gates. There will be forget gate, input gate, output gate. The input gate, the new word, the new what you have the data is coming in the input gate. There will be an output gate that is producing something that has to go to the next one. Now what is new in here? And that is dealing with that gradient problem. What is? It will be the forget gate. So this is an important gate now here that we are using in order not to memorize everything. What is not relevant, we are not memorizing. We have to memorize what is relevant. It's similar to when you read a book. So you keep some notes and you memorize the most important part. The same happens in the sentence of Greece. So maybe you don't need to memorize all of them, we need the Greece. Greece in order to understand that the missing word in the sentence, it was Greek. And this is the powerful of LSTM, or because they are dealing with the gradient problem. And how they are doing it? Introducing the concept of a forget gate. Okay? So, now in here we have also everything has drawbacks, so advantages and disadvantages. Let's say the same is for LSTM in here. So they are almost of handling long-term memory issue that we have. They are superior in high complexity language model. They are, and also as I mentioned to you, for example, we have done a lot of testing in terms of doing a sentiment analysis with polarity and so on, and you're using LSTM and so on, and they are really good and powerful in being used in different tasks and so on. But they are bigger computational cost and they have more parameters and so on. So now from the LSTM that you see, this is this kind of neural network. We have another one which is a gated recurrent unit, the other one in here. have a look in it, and if you can compare a bit how they look like, what is the main differences, and how many gates do we have? In the LSTM, we have 3 gates, the input, output, and the forget gate, that is going to decide if you want to memorize or not something. And in the other one, in the gated recurrent units, what we have? How many gates we have in there? It's a simplified version of LSTM. So it's based on LSTM, but we try now to simplify that architecture, and we come up with the gated recurrent units, which is a simplified version of one. How many gates do we have now? So, in here, so this will be the output. This is what when we process. And now, based on the forget gate, we need to know if we want to keep it or to forget it, let's say. This is 3 gates. Now, when it comes in here, how many gates do you have in the other one, which is gated recurrent units? 2. Okay, so it's 2 rather than 10. But what is the simplified version? What do you think? What it was one of the main drawbacks of LSTM that we ended up with considering another architecture that it will be simplified? Due to what?
Due to complexity.
The main challenge that we have in deep learning, you know, is that one. Heavier computational costs and more parameters. So they are performing good. We get a very good results. We are happy with the results. But the main drawbacks that we have is about heavier computational costs and a lot of parameters. So now we want to simplify them, because sometimes simplifying them means that we can achieve almost the same, most of the time maybe not the same results that we get with LSTM, but almost the same, but what? They have few parameters also, and often they achieve a similar performance. And that's why we try to simplify the architecture of LSTM in order to end up with other networks that they do almost the same, so in terms of the performance, let's say, but they are faster, because you know how computational they are in terms of the parameters and so on. So, preparing the data now. And this is something that you'll do in the lab today, and also with your project and so on. What is the language of computer? What does the computer understand? Binary, 1 and 0. Yeah? So now, if I have a textual data, so the sentence, the film, the movie was not good. How the computer will understand? Should I do something? What happens? What do you think about it? How can I process this textual data? How to change to it? So he's saying that you have to change it to binary, yeah? So the computer doesn't understand the textual data, okay? So now I need to find some ways in order how to present them in a numerical way. So we have some numbers, okay? Because the computer, or when I say computer, it means an LSTM. So if I want to use the LSTM, you might have some codes in Python with the architecture of the LSTM, the model itself. But what? You cannot just use the textual data that you have in a text file in order to feed in a neural network, in a neural network. So you need to process this textual data. And this is what we say about preparing this data and so on. There are many ways of doing that. So sometimes in NLP we can go for some simple methods like backward works that we call it, which are feature extraction. We create some matrix with numeric values in it. So the text is converted into numeric values, and after that we use these numeric values in order to fit in the models. It doesn't mean it's not. It can be even other models like super vector machine learning and so on. It can be neural networks and so on. But the first step is about preparing the data itself, okay? Because text should be converted to numeric values in order to continue and to use that in any machine learning or deep learning model that you want to deploy. So you will need to transform your data, your textual data, okay? There are many approaches in NLP and so on. It takes some weeks in order to introduce students in details, but this is out of the scope of what we are doing and how you can convert it and so on. In this example, we are bringing the concept of word entities, which is a spatial transformation in that one. And if you see the vectors, this is a classical example in NLP about how we can present. What do we have here? Do you see that we have some vectors? Yeah. You see the vectors there? King, queen, women, men. Yeah? Okay? So now behind the word embeddings here, and there are different techniques, word to vec, glove, and so on, but I'm not explaining and going into details because it's not the scope of the session today. So as the recurrent neural network, but even any other machine learning model cannot process the raw textual data, we need to transform it. How to transform it? We are going to use different techniques, and one of them is the word embeddings in here. Words now are converted into numerical vectors, but what? With this technique in here, and you have to look a bit at the vectors, how they are presented there, what we want? We want that semantically similar words appear close together. Okay? So what does that mean? It means that from the vector point of view in here, the difference between, in here, the difference. Now, can you tell me the difference between king, queen? So, it will be, they should be closer because what? Because they belong semantically what they represent. They represent royalty. Now, when it comes to men and women in here, what do you see?
Bigger difference.
Okay. So, do you see any difference? So, if I'm asking to you now, based on this vector representation in here, so what the difference should be identical between them? What difference in these vectors do you think that should be identical?
Between woman and queen should be identical. The distance as between man and king. Do you mean?
What do you think? What it will be here? Yeah. What you are saying? The difference between which vector?
The difference between woman and queen should be identical as between man and king.
Yes. Okay, because semantic. Okay? So this is a representation here. Now what happens when we do this work, when we create these vectors with numeric values, and also yesterday it was Lois that was talking a bit about padding even in the images and so on. So we can end up with some that they are different in terms of the length. Okay? So what we do now? We sequence padding, we call it, because we want to end up with having a structural uniformity in that. So we are going now, as if the sentence varies, and now we are going to fill in with some zeros in order to end up with a structural uniformity. Anyway, I'm not going into details to talk about how the word embeddings works and so on. Today in the lab you are going to work with it, but we'll run some code in order to do it and so on. But keep in mind that the raw data that you have, the textual data, you need to apply some techniques. There are so many of them, as I mentioned, globe, word to vec, and so on, in order to transform. And what happens during the transformation, you'll end up with some numerical vectors, okay, where the text is transformed to numerical vectors, but keeping in mind that if we go for the word embeddings approach, in this one, we are going to semantically similar words will appear closer. So, in order to keep the context, okay, that is important. So, something that you have to understand is the pipeline of processing this textual data, and this is what we will do today in the lab. It's important to understand the pipeline. The first one, you are going to have a text. This movie was brilliant.
Do you mind if I
interrupt?
Yeah. We had a very interesting question here about the length of the sequences. Remember, Gerda talked about, so there are sequences that definitely they do not have the same length, right? Each observation that comes in doesn't have the same length. We're talking about social media or documents or whatever. They definitely have different lengths. And then for us, we need to make them have the same length. And therefore, we are adding zeros. Now, the question was that, should we always monitor the largest length and then add the zeros to anything else in order to reach the maximum length? This is not always the case. We shouldn't do that all the time. We set up the length at the beginning, and typically we say the length would be 256 or 512. Remember, the more inputs we give to the RNN, the more complex it becomes. So if one document has, let's say, 2,000 words, do we really need 2,000 words in order to understand the sentiment of that text? No. So we can select for all the sequences to be 512, and for this document that exceeds 512, we can just remove the rest of the words. Okay? So now for the other texts that are less, we just pad 0.
Yeah, and that happens in the Python code. When we write the Python code, so we specify the maximum of, because this will be a matrix, let's say. So once we transfer the text, we will end up with a matrix with numeric values into it. And one dimension of the matrix we specify as a maximum 512, for example. And we work with example, an Obama speech is a long speech, let's say, but we cannot keep all. It can be 3,000 and so on, because it will be a very big matrix and we cannot process, and due to the computational power and so on. So we specify that the maximum it will be 500, and we end up with having that 500, yeah. 512 usually. So this is important to understand this pipeline. So this is what we'll do in the lab as well today. We are going to have data, text or data. For example, this movie was brilliant. There will be more sentences there and so on. What you have to do now? The process of tokenization, you can see here and understand what tokenization is to split. So we are going to split now the words, the sentences will be split into words. We have, in the first one, this movie was brilliant. It will be tokenized. So each word now is a token. So the first one, this is a token. The second one, movie, is a token. The third one, is a token. Brilliant is a token. So now, from one sentence that I have, I end up with 4 different tokens. Okay? So now you told me that, you see, yeah, the matrix that I was explaining right now. So now each of these words, using some techniques, and there are some very simple ones for feature extraction, like a bag of words, which is the simplest one, but we are doing here ambiguous techniques that are more advanced. We need to convert now that words, the token itself, to numbers, because the computer itself, the models that you will deploy and so on, need as an input numeric values. They cannot get text. So now we are doing the embedding process, and we end up with the embedding layer. So now each of these tokens is now translated, let's say converted to numerical matrix, okay? And now this is going to be an input in what? In our LSTM or in the recurrent neural network or in any model that you are deploying. It will be the input. And what? At the end, because here you are going, it's important to understand it's the same, similar concept like in the convolutional neural network. So there are 2 processes happening. So the LSTM itself is doing the processing in terms of understanding the context and the semantics in the sentences. But the last one, there will be a dense output layer that is going to do the process of what? Of classification, because we want to classify, you know? So we are doing a sentiment analysis. So it will be a classification in here. So there will be, so the output from the dense layer using any activation function, it can be sigmoid because this is what? This is a binary classification. We can use sigmoid. You can also use softmax, for example, if you have more than 2 sentiments, positive, negative, and neutral. And there will be also the dense output layer that is going to do the classification in the process. So let's say the pipeline here, what is new compared to the images and so on. So you need to understand that everything that you have to tokenize, create your tokens. Tokens are split into words, tokenization process. All this using some embedding techniques that there are many different of them. You need to convert it to numeric matrix, and they will be fitting in the LSTM, recurrent neural type of recurrent neural network, and in the lab we work with the LSTM, and there will be a final layer in your network that is responsible for the classification, because in this example we are doing a sentiment analysis, depending on the task, let's say, but the example here is about the sentiment analysis, and the dense layer is going to produce, to classify all the records, or specific records, if you want to test it for different of them. So in terms of belonging to the positive sentiment or belonging to the negative sentiment and so on. So this is the whole pipeline, okay, that works. Now if I go to the last slide, it's about what you will do in the lab. So, the transformer. I'm skipping the transformer for tomorrow. Is it okay?
Yeah, maybe we won't talk about transformers.
So what?
Maybe we won't talk about transformers at all.
We will not talk.
No.
Okay, so I skip transformers for the moment. I'm keeping it just to LSTM.
One question related to the conversion from token to numbers. There were also differences in the colors in each cell. So what is that connected with the quantity of the number or the color? Green, gray?
No, I don't think that there is
No,
something.
no, that is just
It just is to visualize.
yeah, random.
Okay.
We can stay here a little bit. I can
Yeah,
make a
you can.
historical note
Okay.
about this. I mean, this is a great slide because what you see is actually we see the different components of this pipeline, right? And Ogerta nicely described the LSTM RNN component. We skipped a little bit the NLP, but I'll make a historical note about the NLP because maybe it's important for the project since it's an NLP project. So the dense layer is actually the classification part, which you already know. CNNs, at the end we had a classification part. Here we are, same thing. LSTM is a different architecture, similar to CNNs like we did yesterday. Done. We understand what it does. The first two pieces are actually the really important pieces here that take you to the application. Okay? And as Ogerta mentioned, when you have text, for example, there is no way that the machine learning algorithm can understand words. So one thing that we should do is to convert the words into numbers. Okay? And now there are tons of different ways of doing so. So for instance, the most traditional way to convert the words into numbers is counting. Okay, so you have a collection of documents. You are just getting all the unique words from those documents, and then you are just counting how many times each unique word appears within a document. Is that clear? Okay, what do we produce from that? We produce a two-dimensional matrix where the number of rows are the words, the unique words, could be, let's say, 2,000 words, unique words within a corpus, and the columns will be the frequency. Okay? This is counting.
Bag of words.
Bag of words. It's called bag of words. We are counting how many times each word appears within the documents. Okay? It's a very, very traditional technique, and it's still very, very powerful. Sometimes more powerful than embedding techniques like what you see over there. However, there is a big disadvantage with those type of methods, with counting. The disadvantage is what we call in machine learning sparsity. Okay, so sparsity means that within a vector, if you go to that matrix and you extract a vector, right, you may end up having a lot of zeros within that vector. And you would imagine that for the whole matrix, you will have a lot of zeros there too. Okay. This is a big disadvantage for any type of machine learning algorithm because it cannot handle nicely all of those zeros. And do you see why? Remember, you want me to
No, I just want to add something
Yes,
because I
please.
think this is something that I explain in very details in my module, but you'll get confused. So suppose that you have this movie was brilliant. So how the matrix is created? As Joyce was saying, all the list of words, it will be rows in your matrix. So it will be this movie was brilliant, Ogerta, because the text is longer, President, Obama, all these things. Now, in the other one, this, does it belong? Sometimes you can count how many times, or sometimes we do it binary. It belongs to that. We put 1 in the matrix. In the other one, 0 is not there. Because not in all sentences that I have the word appear. President, it was only in the first sentence. In all the other ones, it would be 0 because it doesn't appear at all in the other documents. Okay, it was just 1. It's a real word in the document. So I'm going to have now a row in matrix that will be all with 0 because it doesn't appear at all. That's why you end up with a very large matrix but sparse, so many zeros into it, because there are some words that they are not frequent at all. And this is one of the drawbacks of this matrix, of having so many zeros into it. 1. The other one is that we have also about the importance of the words. For example, I bring an example to my students. We have 3 sentences talking about the hotel, reviews of the hotel. When we create that matrix, the count for the word hotel itself, it was 4 or 5 because it appears many times in the reviews. But the word hotel itself is not relevant because we know that I'm processing some data related to the hotel. So I want to exclude that hotel word because it's not relevant. Even the frequency is very high. Okay? So these are the 2 drawbacks of bag of words method. And now, in order to solve it and to deal with backwards, we use DFIDF. So you can continue if you want to talk about DFIDF.
Great. I'm going to talk about DFIDF. You have a question?
About the order of the parts of the sentence, or like so, and second about some characters or some conjunctions or mixed or small parts that are very frequent.
Yeah.
So when they are converted into binary, this is the most large problem.
Yeah, yeah. I'll get to this. I think this is very important what you're saying. And even within English, this is a challenge. I can say why, but before I say why, I will talk about why sparsity makes things challenging for the machine learning algorithm. Remember, we create those matrices, right? And then the features for the machine learning algorithm will be the words. Okay? And now we have the documents being the observations. Now each feature now will contain a lot of zeros in the space of the documents. Okay, now that immediately makes the features highly correlated. They look very similar to each other. Okay, so when features look very similar to each other, that means that we are talking about high correlation. And high correlation is actually affecting the performance of any machine learning algorithm. Okay? Now then, therefore, that's why we have dimensionality reduction techniques to remove this high correlation from the data. Okay, now I'm going to that point here about different languages or even within English. There are a couple of words that could appear many times. You know what? A set of words that appear many times, it's actually stop words. For example, the word I, the word and, the word the word you, and so on. That appears frequently, okay? More frequent than other words that would be very important, like Barack Obama, for example, like a hotel, for example. That's why what we do, and this is actually very important in NLP, is stop word removal. So there is a predefined list of stop words within a package, a library, Python library, that you actually load, and then you pre-process all your text by just removing those stop words. From the list of stop words, you identify where they belong in the documents and you get rid of those. You just remove them before you even start doing machine learning. Okay? Now, you mentioned Albanian. And I don't speak Albanian, but I understand that the language is difficult by itself. Okay, it has many challenges. And I'm not going to the cultural side, but I'm going to one important thing. English is a widely used language, so machine learning engineers have worked a lot with English, and they have solved those issues. Even the stop words, they have a predefined list of stop words which they load in NLTK. Okay, that's a Python library. But when we go to Albanian, there are not. And if it is, probably it's not the full list. You may see the list and you say, okay, they forgot this, they forgot that, blah, 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 right? So that makes things challenging beforehand. So that means that you as an engineer, and you will see in the project, you have to probably come up with a list of, or predefined list of words that are spelled differently, they have the same meaning, there are stop words, and so on. Anything that is actually tied to the language and you think that it will affect your final pipeline. Okay? Now, yes, good. So historically, I want to say something also about the embeddings. So
Just to
maybe,
stop words, let's say. So in terms of cleaning the textual data, because we call it pre-processing and cleaning, we have to make sure that we do the proper cleaning, because what happens? You can remove some of the stop words. For example, not is going to be removed during the stop words and so on, but it's going to impact your sentiment analysis. So it's not a one task again, so not always the same cleaning happens, depend on the task itself. Sometimes removing some stop words might have impact in your sentiment analysis as well. Or it can also, there is sarcasm in the textual one when we do sentiment analysis and things like that. And we have to properly clean the text, but there are some steps that we follow, like Zois mentioned, about removing stop words, we do emblematization, stem, and so on. But still, it depends also on the task that we want to do, and we have to carefully consider, at least when we are doing sentiment analysis, because this kind of stop words and what we do in stop words is filter out, so remove this kind of words. Why? Because they are not relevant, they do not contain any information, but also that matrix that we are talking about, dimensions, it will be reduced if we remove all these stop words. But we have to consider and carefully filter out these words, because sometimes we need this kind of words because they contain context into the process that we are doing and so on. Yeah.
Do we use the frequency of words as an indicator to what can we remove? What word can we remove?
No, it's not about it. It's like when I say filtering out of stop words, there is a library, NLTK, that we use in Python, and it has a list depending on the language, let's say, where there is a list of stop words, and it's just doing it like a rule, let's say. If the word is not and it exists in that stop word list, filter out. This is what happens as a process.
I'm saying for other words, do we use the frequency of the words as an indicator so we can also remove other words we know, or not to memorize those if they are not relevant?
I think I understand the question.
What about the embedding?
Yeah, so
Yes.
I think when we have a collection of documents, right, and then you are extracting the unique words from that collection, then you can actually go and count how many times a word or the words appear. So then, I think what you're saying is that keep the unique words up to 20% or above 20%, or keep only the most 20% frequent words of the corpus. Yes, that can happen. Just to answer your question with a yes or no. Yes, it's an indicator.
We can use the frequency as we're saying, but sometimes we use also length of the word. As we have so many words, for example, I tell to the students when we run this kind of example, so filter out all the words that they are less than 2 or 3 letters, for example. It's like, reducing it. This kind of, we do it.
Highly depends on the application you are working on. For example, this application which is positive or negative sentiment, which is a binary classification problem, we can do this to reduce the dimensionality of the feature. Because each word will be a feature eventually, if we do count. Okay? But it really depends again on the application, because if you really want to identify names, or if you want to do translation, or if you do generation, then it becomes trickier. I may go to another historical. Since we have time, and since the next thing is forecasting, which we may not go very deeply, we stay at NLP. But I made the historical note. So we said counting, right? Counting is the number one, or how it started with frequencies, and then as Gerta mentioned, DFIDF, which is important. But then, as we mentioned, those vectors that we are collecting and generating are very sparse, highly dimensional and sparse. So people thought, okay, can we actually take into account context rather than single words, single entities, and count? So what they wanted to actually get is how other words influence a particular word. Okay? And the way they actually did that was they introduced deep learning for that. and they start making predictions. So from surrounding words, if there are inputs to a neural network, can we actually make a prediction about a given word? I live in empty and the weather is very sunny. Okay? So can I get the surrounding words and predict the word in the middle, the name of the country? Could be Albania, for example, because it's very sunny. Okay? So can I inform the network from the surrounding words and make a prediction about the middle word? So this historically was called word to vector. Gerta mentioned the model. It's a very shallow network, input, hidden, output. Okay? And it actually gets the input from the surrounding, it does something in the hidden layer and outputs probability values for words that could be candidates for the middle word. Okay? Then glove was another technique that was mentioned, which was very simplistic, and everything was great. Then RNNs actually played a huge role in history on NLP tasks. Like Gerta mentioned, all of those many to many, one to many, and so on. 2017, we had a big revolution. There is something called attention. Okay? And there is another model that was, we're gonna say, there is another model called BERT that came up, and attention, 2017, that was actually the historical time. Because with attention, which is actually a big, it's a notion or it's a terminology within the deep learning era, within the deep learning field. The people actually were able to improve all of those models, okay? And they introduced transformers, which is actually why today we are able to use ChatGPT in that way.
Yeah. Do you know what, for what stands GPT? What GPT means? Generated, pre-trained, transformer.
Transformers,
So
exactly.
it's a transformer, okay?
Generated what?
And
Pre-trained.
GPT was even before, right? It was
Yeah.
even before 2000. It was GPT-1, GPT-2. If you see the outputs of what the machine was extracting was completely off. But then, with more data and attention, people actually figured it out, and they made actually those models, the huge models, LLM models, work nicely. And that's why we have today these nice outputs in our ChatGPT. They are so intelligent, they can handle everything. Okay? And again, simultaneously, they can handle different tasks as well. Because I can use a dialogue system like ChatGPT, and I can ask I can give one prompt, which is summarize, and then I go translate. Okay, so these are two different tasks that can handle simultaneously. You want to say something about transformers?
It's like the first one, let's say, about recurrent neural network. It's like where we have been children and we have played with telephones, let's say. So what happens? I'm saying something to him, okay? He's adding, adding his own words, and he's passing through the other one. So this is the first one. This is how it happens with recurrent neural network. Now, in the other one that we are talking about transformers is the attention. So, rather than being in a sequence, why? Because it's time consuming, let's say. It will take time to pass through the whole sequence, the telephone line. Okay? What we are doing, let's sit in front of us, each of them, and let's start to communicate. So, this is the difference, let's say, in terms of the shift in transformer. So, here, that is a transformer.
Yeah, I really like the example that you gave about this rounded table, because this is exactly an RNN, right?
Yeah,
we can actually enter this room, and as we enter, we can say something to you, and you can pass it to your friend.
But you add something. You also can incorporate your own words to that one.
Exactly.
You have the memory. What he's saying to me, this is the memory. I add something, and I'm passing through. So this is a recurrent neural network. Here we can do it.
And now we have 60. I mean, you will see in the code 64.
But
that means that we are 64 people within that round.
It's time consuming because the guy,
the broken phone.
the broken phone, but it's time consuming because they have to wait now. Okay, here we are not waiting at all. Let's sit in front of us and let's start to talk all of us. This is attention.
And you can
Okay,
pass
this
it
is a
wrong, like
transformer.
the broken phone, I think.
Yeah.
You can also pass it wrong, so
So-
you might lose some data
Yeah.
along the way.
Yeah.
Yeah.
Same practically as not in the kinds of jobs, but applying in computer architecture where we have parallelism of the jobs, specializing every task, making it.
Yeah. Though I like this example, in parallel computing we do not actually make predictions, but the problem in parallel computing is communication. So I have, let's say, 64 workers working on a specific task, which I broke the jobs into little pieces. Then they execute each, but when they execute, they have to communicate properly because otherwise the result that we are getting is poor, right? So say, for example, and when we do parallel computing, the first example that we always, or I always do, is matrix multiplication. Matrix multiplication is a task that can happen in a serial way or in a parallel way. But the machine should actually be intelligent enough, or I should program the machine, by the way, to be intelligent enough to get all the inner products and then take them together and get a unique answer for me. Okay? So, same thing happens within TensorFlow. I mean, people who are working, creating this code, they have optimized it in that fashion, right? So that's why now we are able to use GPUs, TPUs, and blah, 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 all of this great stuff. Okay, we have 10 more minutes. Any questions? Yes?
Yes, I was wondering what happens to words that are never found in the embedding. For example, there exists a word that is very uncommon in the English language. What happens if this goes in our network and it's not trained on that word?
Very good. That's a great question. I'll make the answer a little long because I have to say a lot. I like this question and I have to say a lot. So there are two things. So for example, the movie, I can go back. Here, the movie was brilliant. So say we have those 4 tokens, and now we are going to a pre-trained model because we do not actually train our own embeddings. We will go like we did yesterday into a model like yesterday we did VGG, right?
VGG16.
VGG16. Now we go to another pre-trained model for text. For example, Google, Net, Word2Vec, and so on. These are pre-trained models using, let's say, millions of Google articles, and they are actually coming up with word embeddings for each single word. Now, say that we introduced a new word that was never in that corpus, in that word embedding list that Google has. And I have a sentence. The movie was brilliant because it's a masterpiece. Okay? The word masterpiece is absent as an embedding. What's going to happen if I don't include it? I will include zeros for that word embedding. Okay? And most likely, if I do not have a lot of word embeddings that are missing within this training phase that I'm doing, nothing will happen. It won't affect at all. Okay? Though, if I do have many that are missing, for many observations, for many documents, then you may actually see an impact in the training phase. Okay? So, my point is that that goes again to the application. So, if we are trying to do sentiment analysis and get positive or negative sentiment from movies, most likely absent embeddings won't affect much the final accuracy. Because who cares if I get 98 versus 95, right? So it doesn't really matter. But when I'm trying to make, for example, do detection of hate speech, and I'm not talking about just one sentence that is full of, that is a hate speech, I'm talking about entities within a sentence, named entity recognition tasks. Then actually this may affect, okay? However, and again, when those pre-trained models have been trained and provided to the public, there is a big probability that all of the words that we are using will be included in the list, because they are using millions of documents, everything from Wikipedia, for example. Yeah, unless we are working again in a very specific domain, for example, chemistry could be a specific domain for particular molecules.
So it depends on what you're working on, the precision you need.
Yeah.
There should be a precision level you need to reach.
Exactly,
For that specific.
exactly. So when we are working, let's say, for example, in a medical domain or a chemistry domain, that you are dealing with entities or words that are very rare and you are pretty sure that they do not exist in any pre-trained model, what you can do is actually use the pre-trained model and your corpus and train them together. And do something we call transfer learning from one to another. Okay, so you are moving knowledge from one domain to another domain. Okay, that is happening a lot, by the way, in medical or pharmaceutical and chemistry, because there are some fields in chemistry that are very poor in data, but pharmaceutical is very rich in data. So people used to actually take these two fields, merge them together, and do some transfer learning in order to make embeddings and come up with other tasks. Okay.
So I have just a question, as those were explaining to you, how many neural networks do we have in here?
Pardon?
How many neural networks? LSTM, one. It doesn't matter, LSTM, this is one, yes? You have another one? No, it's not
No, it's
one of
the
them.
same.
Doesn't
It's
count.
one of
It's the same. LSTM is belongs to the umbrella of the recurrent neural networks, okay? So is this one neural network, yeah?
Yes.
Okay? Do you have another?
Tensor players.
What?
Tensor players.
No, the tensor layer is not a separate one. Both of them, this is one neural network, okay? There is a last layer, let's say, but under one LSTM. We consider one neural network. Do you have another? What? In the embedding layer, but what we are doing? Our data we are using to train, and when we say train, to calculate the weights, to update the weights, backpropagation, all the things happens in this. This is the engine that we train and we use our data. When it comes to that embedding layer, we are using some pre-trained models. So it means there is a neural network, let's say, that I'm not training at all. So it is pre-trained. I'm using the weights and so on in order to get this output, this matrix. But saying that there is also a neural network that I'm using, but I'm not training with my data at all. And why? Because I want to convert now all the tokens that I have and to have this numerical matrix. Okay? So just to clarify.
And one other question, are these matrices related to the words? Because, I mean, I can observe that the first row is equal in all four embeddings.
Yes, you are right. So, yeah.
This is like a drawing.
It has to be different, for sure.
There are different. I mean, this is just drawing.
Don't look at the values, don't look at the colors.
Yeah.
But when they are defined, are they related with the word somehow? Or
Yes.
Yeah.
Good.
they are random numbers?
No. They are not random numbers at all. So there are numbers that we cannot really see and observe a pattern, but they are related. So each word, each token has its own vector representation. And all the words have the same dimension in a common vector representation space. So let's assume that each word or each token has a 300-dimensional representation. That means there is a vector of dimension 300 and it sits in a 300-dimensional space. Now, as you saw in the previous slide that Ogerta showed with a man, king, and blah, 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 so that means that a man could be represented in a 300-dimensional space as a vector, and in that same space, woman is another 300-dimensional vector sitting there. Now, one thing that we can do with actually high school mathematics is that measure the distance between those two vectors. First of all, we can take them together and then measure the distance like this, right? In an n-dimensional space. And we can observe that if two words have similar context, then these two vectors will be close to each other in a sense of a Euclidean distance, for instance. Okay, there is a big discussion about how to measure, okay, but maybe I can make a parenthesis about how to measure. So I said using Euclidean distance, right? So Euclidean distance is actually going from one point to another versus a straight line, right? This is under the assumption that those vectors are living in a flat space, right? Because if we assume that the vectors are living in a curved space, then I cannot actually go by a straight line. Can I? If, let's say, I assume that two vectors are living on a sphere, can I just measure their distance by just taking a straight line? No, right? I cannot just enter the earth and go. So what we do is actually we measure by the curves. So this is another way of measuring, and this is very relevant to NLP applications too. So this is called geodesic distance of two entities. But in NLP there is also one more thing that is very important. It's the magnitude of each vector. So it could be like a vector representation, could be the word for the word president, okay, could be very long, okay, and another vector that is about Obama could be very short. All right, what happens now if you take the Euclidean distance between a very long vector and a very short vector? The distance will be very big, okay? However, semantically, Obama and president are linked together. Okay, so then people thought, okay, I need to change the way I measure things. So instead of using Euclidean distance, I'm gonna use the cosine similarity. So I just measure the angle between the two vectors, which doesn't really care about the magnitude of the vectors. One could be long, the other could be short, but the angle always remains the same, okay? So these are things that it's important to keep in mind when you're working with these applications, because measuring distance is as important as tokenization. I can bring it in that analogy. It's very important, all right? You can, you can lose the point if you do not measure the right way. And that's true in reality too, right? I can measure this distance with my hand, and I can measure it with my feet, and then I can take a tape, right? And I will be more precise with the tape rather than with my hand. Good? Same thing happens in those applications too. Okay, it's 45, so let's stop. Yeah.
Coffee.